Good morning. So I hope you are settled in. So we were discussing two-port networks, nonlinear two-port networks in the previous class. And then we graduated to saying that since we cannot express I1, I2 in terms of linear relationships of total V1, V2, because it's nonlinear, we can express the incremental quantities. We can express the incremental quantities as the linear combination of the currents or the voltages. So essentially what we did was we said this is V1 plus small v1, this is I1 plus this. And the relationship between the incrementals can be expressed as and we also talked about some of the other forms where the relationships between I1 and V1 can be expressed like Z matrix and ABCD parameters. And if you look into the literature, there are a couple more. But in this course, we'll be mostly concentrating on the Y parameters. Now, note that why we are interested in doing all these small signal parameters, or the small signal parameters are, or incremental parameters represents change, right? And when you want to transmit any signal, a signal essentially is what? A signal is representing some sort of change, some sort of time varying. There is a time varying notion to it. If there is no time variance, I mean, if everything is flat, there is no signal, no information is getting transferred. So in essence, there is a merit towards figuring out how a system will respond when it is perturbed with change, right? So in our context, we have a signal source maybe, which also can have some internal resistance, and I have a load RL. And what I would like to do, I would like to have a voltage power amplification from V in to RL. I mean, that has been the goal for quite a few classes. So the goal hasn't changed. This is what we want to achieve. And we said that we have to put some network in between. And then we argued that this network has to be nonlinear. And because it has to be nonlinear and all, we have been doing all sorts of analysis. And now that we have a framework to analyze, what we can do is we can use that framework to figure out what other properties of this network, or in other words, now that we know that this network can be expressed in terms of Y parameters, incremental Y parameters, essentially what we are asking is that, is there any any good old Y11, Y12, Y21, Y22 will suffice, or we can narrow it down, or there are some particular characteristics of this Y parameter matrix that we require in order to get power amplification. So that has been whatever we have done till now has led us to this point that we have narrowed the problem down to a set of incremental parameters, and now we are trying to figure out whether these incremental parameters need to have certain properties in order to get what we want. Now, when we sketch everything in terms of incremental parameters, you should have it in the back of your mind that these incremental parameters are a function of the quiescent point at which my nonlinear network has been set up, right? So what I'm essentially trying to say is that, I know I'm being repetitive, but it's probably worth mentioning once again. So these nonlinear networks are a function of some quiescent voltages, V1Q, V2Q, I1Q, I2Q, and this is some V1, V2. Okay. So, and in order to set these up, in order to set up the network in terms of V1Q, V2Q, I1Q, I2Q, you need some voltage source, you need some battery. Okay. So we also had argued that we need a battery. So maybe you have a port inside which you can take out and add a battery. So maybe you can do that. Maybe these input ports or the output ports have. What I'm trying to get at here is that this battery need not come from a separate port altogether. It can be also a function of so it can also be this DC supply can also be connected to any other port. It can be the DC supply can come along with V in. It can be attached to V2. But the moot point is that you need another DC supply to set up these quiescent points. Now, once you have set up these quiescent points, I can forget about anything that is DC. I will evaluate what are my incremental parameters, and will behave as if this is the network that exists, and the background network has faded away. Right. So the only purpose of going from the only thing that I require to go from here to here is I will use quiescent points to figure out the Y parameters. And once I have figured out the Y parameters, we'll assume that the background network exists, but that is not something that we are concerned about as of now, because all the analysis will be done in terms of Y parameters. Okay, does that make sense? Does that make sense? Okay. Yes. Somebody had a question? Okay. Can you repeat question? Okay, so these terminals, we call it as V1, V2 terminals, right? Yeah, Q means quiescent, right? So, yeah. Okay, fine. So now let's move on. Let's move on to figuring out what this is. Okay, so as you will see that since we are dealing with Y parameters, it is always, algebraically less messy to deal with conductances than resistances, because you don't have to do V by R in terms of you can do G times V. So what I'll do is I'll convert this input side into a current source. Basically, I will normalize the input side. I'll convert the current voltage source and resistance series to a current source and resistance in parallel. So this remains as is. So this becomes VI GS, this becomes GS. This remains I1, nothing has changed. If this was I1, I should be in small, you could use small notations, right? Okay. So now let's rewrite my current voltage equations. So this is still V1, this is still V2. So my new I1 is VIGS minus V1GS, right? So if I do the KCL here, that is I1, which is equal to VIGS minus V1GS. It basically, if you think about it, it reduces the number of nodes also, right? If you see here, you have this node, two nodes. In this case, you end up with one node. So if you are using KCLs, so one less equation to do this. So this becomes Y11 V1 plus Y12 V2. Okay. So I will club all the V1s and V2s together because it's, it can be easily expressed in a matrix form then. So this becomes VIGS equal to this is one equation, and at the output side, my I2. So I note that I2 is equal to minus V2 times GL, right? The direction is minus because the current has been denoted in the opposite side. So minus V2 times GL is equal to V1 plus V2 V2. So if I write in a proper way, this becomes so this equation and this equation in a matrix form. Essentially, we are trying to, figure out what are we trying to figure out? We are trying to figure out what is the relationship between the voltages at this node. That is, we are trying to figure out V2 over VI. Right? Because if I know V2 over VI and I can show that there is an amplification, that is essentially what we are after. Right? So if I write it in the matrix form, what do I get? I get and now if I have to find out what is V2 in terms of VI, I can use Kramer's rule to and what do I do on top? You know Kramer's rule? Okay. So the second column gets replaced, right? So this becomes so this is minus some questions? Okay. Okay, this is all maths till now. Nothing to do with specifically circuits. We'll have to now see what does this essentially mean. So we ended up with V2 over VI to be equal to minus Y21 GS by this denominator. Okay. So far, so good. Okay. So this is all algebra, but this is a circuit design course. We have to make sense of why this makes sense, right? Or is there any, how do you figure out whether you have made any mistake? So to do that, we'll have to express these Y parameters in terms of what it means to be, what it means if I have a Y parameter, I want to visualize it in terms of a circuit format, right? So for that, let's write down the Y parameter equations once again. So let's concentrate on the first, on this one. So what is this telling you? This is telling us that if V2 equal to 0, right? So I have a port, I have two ports. If V2 equal to 0, then the relationship between I1 and V1 is resistive, right? Assuming Y11 is positive and real. Let's limit ourselves to Y parameters being real and positive. So in that case, the relationship between I1 and V1 is that of a resistor, and the value of the resistor is 1 over Y11, or in other words, it's a conductance of value Y11. So this becomes Y11, right? So what is that second term telling you? What is this term telling you? So this looks like, and this is telling us that the current that I am drawing in from port 1 is proportional to the voltage that I have applied at port 2. Right? There is a transfer. There is some transfer of information that is happening from port 2 to port 1 in terms of current, and this is a transconductance. And this is the transconductance, and note that if I only concentrate on that, this is essentially I1 equal to Y1 to V2 under the condition as V1 is shorted, right? So if V1 is shorted, I don't I mean, if V1 is shorted, do I have Y11? In the sense that will this resistor that I have across Y11 matter? No, it will get shorted out. So whatever current that will get because of this relation will flow through that short. Okay. So, and this current, how do I model this current? This seems to be a current source, right? This seems to be a current source, which is the current is proportional to the voltage across V2. So it's a voltage controlled current source connected at terminal 1 across port 1, but the control knob is at V2. Okay. So this essentially looks like this. The direction of the current is going downwards because I have expressed I1 in the direction that is going inside the port, right? So this is Y12 V2. Okay. So now similarly, if I concentrate on the second equation, that is this one, what will I get? The easier one is Y2 to V2 to figure out, right? So Y2 to V2 is what? It's a linear relationship between the current through the port and the voltage across the port, and the relationship is that of proportionality. And if I assume Y22 to be real, then it's basically a resistor of value 1 over Y22, or conductance of value Y22. Similarly, if I move our attention to this term, just like in case of port 1, it seems like I am influencing the current at port 2 with the voltage at port 1, right? And how am I influencing? I'm influencing in a proportionate manner. And this is essentially a voltage control current source of proportionality factor of Y21. Make sense? Okay, so last one is Y21 part. Okay, so let's concentrate on this equation. So what is this telling us? This is telling us that the current in port 2 is directly proportional to voltage across port 2, right? So, and also there is an extra current that is flowing in, which is proportional to the voltage across port 1. So now voltage across, if it's directly proportional to voltage across its own port, that is a resistor. That is the Y22 V2. But if it is proportional to some other voltage at some other terminal, then obviously it's a dependent source. And since this is spitting out current, and the current is proportional to the voltage across port 1, it's a voltage controlled current source. Right? So again, this is a current source because obviously the output is a current, and the dependency of the current source is with respect to the voltage, not across its own terminals. A current source which is dependent on the voltage across its own terminals is essentially a resistor. But if a current source that is dependent on the voltage across some other terminal is a voltage controlled current source. Okay. I mean, you will also see later on that these type of configurations have a role to play, in the sense that I could have, instead of Y22, I could have said this is a dependent current source. And this is Y22 times V2. Right? So I could have said that, and no harm done. I have not done anything that is wrong, incorrect. But note that since I have expressed this in terms of Y22, V2, whereas V2 is the terminals across the current source, then essentially I can say that if I have a current source this is no different from a resistor of value which is inversely proportional to the proportionality constant of the resistance. Okay, so these two are equivalent, and we have done this while we are doing source transformation. We have used this principle once. You will see that this is there is a specific type of circuit. When we go to transistors and all, we'll be using this type of configurations, and we'll be replacing these with resistors multiple times. Yes. No, I didn't do that. I replaced the current source with the resistor. So since the question came, so what I'm trying to get at here is that if we just concentrate on the equation, it seems like I2 is sum of two current sources. Right? One current source is dependent on some other port, and the second current source is dependent on the same port. Now, if a current source that is dependent on the same port, then I can as well say that I'll replace the current source with a resistor. That's all that there's to it. Okay. Okay. So if that is the case, I can now forget about the Y parameters in a matrix form and go to circuits. So this is Y12, V2. Okay, and let me rewrite the expression that we got from here, right? Oh, okay. Okay. So now we have to, what I plan to do is try to convince you that we can massage this equation in such a way that we can get some condition on maximizing V2 over Vi. So the easier thing to do is to start off with the terms which are in isolation. So what do you think? I mean, what is the maximum V2 over Vi that I can get by massaging this equation? I mean, I want to maximize V2 over Vi. I want amplification. Right? What is the maximum that I can get? Why?
Because linear.
It's a linear in incremental sense. Overall, it's a nonlinear network. Right? So one might say that, hey, I can. Yeah. So if I concentrate on this term only, then I can say that if I maximize Y21, there seems to be a possibility that I can maximize V2 over V1. I'm not saying this is a local maxima or absolute maxima. What I'm saying is that if I want to increase V2 over V1, it seems like I can simply keep on increasing Y21, right? But I mean, you might have already noticed that there is a negative sign here. Okay. So right. Exactly, right. So what he's trying to get at here is that one can argue that I can set the denominator to 0. And I choose these parameters Y11, Y22, GS, GL in such a way that denominator goes to 0, so I can get infinity. Right? Mathematically, it's possible, right? There's nobody stopping us from doing that. But there is an issue to it. The issue is as follows. So, what do you think there is? I mean, even these current sources in this diagram, right? So let's concentrate on this current source. Okay. Right. GS and GL we cannot control. Correct. So that is another reason we cannot do that. But correct. But even if you can take it to infinity, there's an issue. That is the issue that I am trying to allude to now. So let's concentrate on this current source. So what is this current source telling you? Not only that, it's telling you that we are controlling the input port current with the output port voltage. I can also say that there is a feedback, right? There is a feedback information from the output to the input that is getting fed. Okay, right? And if I choose these values in such a way that, if I choose these Y parameters values in such a way that this bottom stuff goes to 0, right? You have a gain of infinity. When you have a gain of infinity, I can argue that I can get an output without giving an input, right? So, and generally, what happens if you get an output without an input? You know what it is called? What type of circuit is it? It's called an oscillator. So at the beginning of the class, I showed you something. Remember? Do you want me to do it again? So what happened there? I was not speaking, but the loudspeaker came to life, right? So it's trying to demonstrate on its own right now. So what was happening? Essentially, now what is Y21 essentially? Y21 is my signal transmission from input to output, right? So Y21 is a signal transmission from input to output, and Y12 is characterizing the feedback information from output to input, right? So your Y21 is transferring this information, and Y12 is feeding it part of it back. Okay. So, and if you massage these terms in such a way that whatever goes this side and whatever comes back are identical, then I can say that I can get rid of the source, and this will be a self-sustaining equilibrium, right? So that is what essentially I showed you. If we go close to that, Y21 is when I am speaking through this, right? This is my input, that is the output. If I go close to it, there's the reverse transmission is gaining strength, because Y21 in this PS system, the Y21 is pretty well defined. I'm speaking into the microphone. There is a wire connected to it, wireless transmission there, and it's amplifying. The reverse is not very well defined. In order to increase the reverse transmission, Y12 I have to go close to the system. If I go sufficiently close to the system, then it turns out that this denominator can go to 0, because Y12 is gaining strength. And this is not that you want. And since you don't want that, you don't want to get into this mess of trying to figure out when the denominator can go to 0. Does that make sense? Yes. Hold on. Yeah.
Will unwanted frequency get introduced with the
Come again?
unwanted frequency get introduced with the denominator 0?
Okay, I wouldn't say unwanted frequency gets introduced. It's essentially for those of you who are taking E250, you will see there's a thing called Barth-Hewson criteria. So that is a criteria that is essentially a case in which you have when you go around the loop, right? So this is a loop, right? So there is an input to output, output to inputs. When you go around the loop, overall gain is unity. Then in a negative feedback system, you can get infinite gain. And that infinite gain can happen at any particular frequency, right? Because if it's what I have done here, I have told you that all these terms are frequency independent. But it did not necessarily be the case. I have started off with frequency independence. All these are real because it helps make the point. But in a real system, none of these are frequency independent. All of these terms are frequency dependent. So as it turns out, then this denominator will be set to 0 at maybe a certain range of frequencies, or a single frequency, or a set of frequencies. So when your denominator gets set to 0 at, let's say, a single frequency, then the oscillation will happen at that frequency. Okay, and that frequency, whatever that be that frequency, that is a function of how the system has been made. Okay, you had a question.
It's like whatever the speaker going back, like
Effectively that. Yes.
that is a white parameter. But
okay. What is this physical thing? The physical thing is a function of how you have set up the system. In this case, a Y parameter is a function of V1 quiescent conditions. And when you are, this is when I am talking about this domain, right? So note that this feedback system is not necessarily limited to electrical systems. It can be a hybrid system. Here it's an acoustic going into electrical, going back to acoustic. The loop is through multiple systems. So when you have to model these things, instead of Y parameters, we will have some other term, other nomenclature which denotes this feedback. And what does this, in that case, what is the quiescent condition? The quiescent condition will be my position where I am at. Maybe incremental on top of that might be these small I, small b's. So if I go sufficiently close, then I am essentially going towards, I am increasing the reverse transmission, right? Because when it's so far, whatever is emitting from there, it's not really going in, because this mic is closer to my mouth than to the loudspeaker. Now, other way to think about it, if I crank up the loudspeaker volume, then the amount of energy that is going into the mic will increase, which means Y12 in this sense will increase, and you will end up in a condition where this denominator is getting to 0. That is the one way of thinking.
if there is no input, but there is
Well, why is it called oscillator? It's difficult to say. If we agree on the term that oscillation means this, then whatever does this is an oscillator. And okay, so if you are asking that, to be honest, I don't know why it's called oscillator. I have to make up something then. It does an oscillation without any input, so it's an oscillator. I mean, that's the best I can do. And as it turns out, I mean, this designing very good oscillators is also another research domain. And people have done PhDs on designing good oscillators. And when you try to design good oscillators, you try to design systems where this denominator goes to 0 under certain conditions, right? So this is not necessarily a bad thing. For folks who want to design oscillator, you are trying to achieve this. Okay, fine. So now if we agree on the fact that setting this denominator to 0 is not particularly a right thing to do if you are trying to design an amplifier, not an oscillator. When you're trying to design an amplifier, trying to set the denominator to 0 is not particularly a good thing. Then, and assuming all these terms are positive, then what is the fail-safe way of ensuring the denominator doesn't go to 0? So I have to ensure that this negative term goes off. So negative term can go off by either setting y12 to 0 or y21 to 0. I don't want to set y21 to 0 because that is what we want. That is a transmission from input to output. Right? I definitely don't want to set y21 to 0. The only other thing that I can do is set y12 to 0. Sorry, did I said it wrong? I don't want to set y21 to 0. I want to set y12 to 0. Right? So y12 equal to 0 to prevent and y21 should be y2. Now, can you comment whether y21 should be high or low? High, as high as possible, right? So y21 should be to tend to infinity because this is the forward transmission. Pardon? Yes, but it will be infinity at DC, right? So what you are trying to, I understand what you're trying to say. I mean, now think of if you have done ideal op-amps, right? Think of ideal op-amps. What is an ideal op-amp? You have a gain of infinity. It's never infinity is tending to infinity, right? As long as it doesn't go to infinity, we're safe. Okay, fine. So y21 should be as large as possible. If you are not comfortable with thinking in terms of infinity, assume y21 should be as large as possible. So that is fine. Now, could you comment on the other two terms in the denominator? I mean, the network in the box? Can you comment on y11 and y22, assuming they are all positive real? What should they be? Very large, very small? Yeah, so then it boils down to how it is tending. How it is tending to infinity, right? So that becomes a limit question. We are essentially saying, I mean, if y12 tends to 0 and y21 tends to infinity, then y plus that product y12 times y21 need not be 0. Right? So then it becomes how I'm tending to infinity. Yeah, but if the denominator goes, so here is the thing, right? So there is something tending to infinity and something becoming set to infinity are different things. Because if something is getting set to infinity, which means that when you're putting it in feedback, there can be likelihood of self-sustenance. Right? That is what we demonstrated, right? So if this term goes to absolute 0, not tending to 0, absolute 0, then there is a self-sustenance. But if there is something that is going to infinity, but not fully to infinity, we have not still hit that self-sustenance thing. Okay. So essentially you can, I can try to set y1 to 0, but any physical quantity you cannot really set to infinity. Right? When you are making it physically, y21 you can try to make it as high as possible. You might want to make 1 million, 1 billion, doesn't matter, but it never goes to infinity. So that way, everything is a positive real quantity. Setting y21 to infinity might be a better option than trying to play around with setting the denominator to 0. That's all. This. Okay. Correct. If y1 is exactly 0 and y21 is tending to infinity, then this will not, the negative term is still 0. That will not go to infinity, right? If y12 is absolutely 0, not tending to 0, is absolutely 0, and y21 is tending to infinity, then the product is always 0. Y12 times Y21 is 0.
Yes, that term is 0 because it's overall term.
That's not a problem. That's not a problem because it's tending to infinity, not exactly infinity.
If Y12 is 0, but the gain is infinity somehow.
So how can that's what I'm coming to. How would you make that gain to be infinity? The only handle down you have is Y21 tending to infinity. It's not exactly infinity.
We want to gain to infinity while keeping Y12.
Correct. Gain tending to infinity again. I mean,
Like it can be as high as possible.
Right. Exactly. Okay. So now, what about Y11 and Y22? What do you want them to be? You want Y11 and Y22 to be 0, obviously. Y11 and Y22. So 10 to 0. Simply because you don't want too much fraction in the denominator, right? That's what this is telling us. But what does that mean in terms of our circuits? Now, Y12 to be 0 makes sense because that is a feedback action. So I want to nullify the feedback. If I can null the feedback, so let me redraw. So this I am nulling, which means the route from output to input is cut off. So I prevent oscillation. Now, why do you think we want Y11 to be 0 other than looking into the, well, let's do the Y22 to be 0 first. Why do you want Y22 to be 0? I mean, other than the fact that it comes in the denominator, can you make an intuitive sense of why do I want Y22 to be 0? Right. So essentially what he's saying is that, see, Y22 is coming in parallel to GL, right? So whatever current is coming out of this source, right? Whatever current is coming out of this current source, I want it to flow into my GL. I don't want it to get divided. If it gets divided, I am losing information. I want all the information to be dumped into my GL. So I don't want any current division. So I don't want Y22 at all, if possible. Right? This is a wish list. Obviously, you cannot do all these things. I mean, maths you can do, you can just say that it's this to be 0, but we have to figure out whether we have something which can do this.
So why, like we can check Y to be 0, like we can open the.
No, when you opening the circuit, set Y22 to be 0. What is Y22? Y22 is a property of the network. The rate at which the output current is changing when you are changing the output voltage. Right? So you have something inside the network, some nonlinear stuff inside the network. So that's why it's not totally in your control. It's a wish list. Still, we are in a wish list. Okay. So if it makes sense that I don't want current division, so I want Y22 to be 0 at the output side. Now, what is Y11? Why do I want Y11 to be 0?
So that the input VIGS flows only through GS.
Exactly, right? So this current, I want to flow into the GS. I don't want it to be flowing into Y11. The other way to, the easier way to maybe visualize is in terms of voltage source. Go back to the voltage source and RS. Essentially, I want all the voltage of the input VI to appear here. I don't want any division. If I have a division, then obviously the current which is proportional to the input port also reduces. I don't want any voltage division across the input port. Because I don't want any voltage division in the input port, I want this impedance to be infinity, which means Y11 should be 0. Okay. So in other words, Y11 should be 0 to prevent voltage drop at V1, and Y22 should be 0 to prevent current division at output. Okay. Does that make sense? Okay, so now your the wish list of your nonlinear network is complete. So what is the wish list? Now wish list is essentially, if I sketch in terms of the wish list is y11 equal to 0, y22 equal to 0, y12 equal to 0, and y21 tending to infinity. Now note that these are all small signal parameters, right? These are small signal parameters in which we are more interested in, but we know that this is something that has come from an underlying IV characteristics of the network, right? So what is the IV characteristics telling you if y11 is 0? Not necessarily, right? Y11 equal to 0 does not mean a current source. Okay, so let me sketch it in this way. So let's say I1 V1 I1 V2 I2 V2 and I2 V1. So when I am saying y11 to be equal to 0, what am I saying is that del I1 del V1 is equal to 0, which means IV characteristic is a straight line, right? So our IV characteristic is a straight line. Sorry. Okay. So I presume this is why you were saying current source. But can I go to the second quadrant? If I go to the second quadrant, what can you tell about the whether this is an active? It becomes active, right? But the stuff inside is passive. It cannot go into the second quadrant. So okay, so as with the start, we started off with the assumption is that there is no source inside, right? Right, there is no source inside, so we cannot have I1 V1 to be in the second quadrant. Okay. Okay, fine. So if this is the case, so all from y11 equal to 0, all we could figure out, all we could rather hypothesize is that characteristics of I1 and V1 should be flat. Similarly, I1 V2, the characteristics should be flat. Similarly, for I2 V2, the characteristics should be flat. But for I2 V1, it should be steep as possible, right? Ideally, it's something like this, right? So this is the wish list. Okay, but as it turns out, all these wishes can't be granted, but there are certain devices which approximate these characteristics to a fair degree, and some of these devices are MOSFETs, BJTs.
When drawing the graph with respect to one voltage, assuming the other voltage is constant.
So MOSFET, BJTs, modern day devices like FinFETs, some gate-all-around FETs, and if we go back in time, your CRTs, or let me just call it tubes. Okay, so as it turns out, all these devices have a characteristics which is similar to this. I mean, obviously not exactly equal to this, but similar to this, and we will get into these characteristics with more detail from the next class. Most of this course will concentrate on MOSFETs, and at the later half of the course or the back end of the course, we'll have some treatment of the BJTs also. So from the next class, we'll get to see how MOSFETs fit into this whole narrative of getting a gain. Okay. Okay.